Hello and welcome back to our sort of penultimate segment in tectonics, which is the anatomy of plate boundaries. We know from our earlier discussions in the class, especially introductory lectures, that we have three different kinds of plate boundaries: convergent, divergent, and transform plate boundaries. And I'll talk a little bit about each of these plate boundaries. In the case of the convergent plate boundary, we can split it into the combinations of different oceanic and continental crusts we might expect to find. And so we have ocean to ocean that we'll talk about in terms of crust type. We have ocean to continent. Change my color there. Ocean to continent. And then finally, we have continent to continent. Each of these is subtly different and has a number of processes related to them. And at the very end of this, we'll kind of summarize the different kinds of processes that we are now aware of operating within or on top of or around the geosphere, associated with the geosphere, and that are occurring at different plate boundaries. So this is a diagram that's sort of our phantasmogram. We have a scale down here from 0 to 100 kilometers. And that's giving us a sense of the kinds of distances that we're talking about. And so you'll notice that if I take this scale and I turn it like this, it also is about 100 kilometers from the top of the arc down to this zone down here where we start getting melting as well. And that's pretty sort of bog standard in the subduction zone, that at about 100 kilometers depth, we start to see melt production in the mantle and the production of magmas in subduction zones. On the ocean floor, over here to the left, we've got a very thin layer of sediments on that ocean floor. And as the oceanic crust moves from left to right in your image, those sediments are scraped off and piled up here in what is called the accretionary prism, or the accretionary wedge. Okay? It is this sort of triangle-shaped blob of sediments that have been bulldozed off of the ocean floor and piled up at the boundary between the two plates. The oceanic trench, which is the deepest part of the ocean, sits here, and it's, on average probably about 8-9 kilometers, but can be as deep as 11 kilometers, where we've got the overriding plate on the right. So that's plate, we'll just call it plate 1 here on the right, and plate 2 over here on the left. And so that deepest part, I've sort of drawn the tectonic symbol, which is a line over the boundary with teeth or pointy things, if you will, teepees, whatever you want to think of them, triangles on the right-hand side. The continental slope, in this case, is submerged off here, and it also makes up this low spot. So this is all underwater, but this is what we call the four-arc basin. A four-arc basin. The four-arc basin is a low spot. It's between the accretionary prism and the actual volcanic arc, the place where we have volcanoes. And in this case, we've got a volcano here, a volcano here, and a volcano here. So these are high mountains in an area that is right next to the coast. So the Chilean western coast of the Chilean the South America, so in the Chilean or Colombian countries, we're going to find this kind of tectonic environment. So we go from the forearc to the arc. Now, behind the arc on the continental side, we're going to find another basin down here. Okay? And this is called the back arc region. So that's one possibility, and that's common when we're dealing with arcs. So we can call it the back arc. Anything back here. or sometimes it's also called the foreland basin. And the foreland basin is an area back here that is going to be before you get to the stable craton. So the craton is crust which is not sorry, let me write that a little bit more clearly. Craton, craton, is crust that is not tectonically active. It can have seismic activity, but mainly there's not a lot of active faulting, active magmatism in those areas. And so the foreland basin is before you get to that sort of stable craton, right? So these are the main parts of a subduction zone. And in particular, this is an ocean to continent subduction zone or volcanic arc. Now, we can change the crust, and what we find is if we change the crust, it doesn't turn out to be much different than this. If we want to look at a quick example of where one of these ocean to continental collision zones or subduction zones is, we can go down to Central America. So here's Colombia, and here is Mexico. And we're looking at a couple of different plates here. We've got the North American plate, the Caribbean plate on the backhand here, or the right side, the North American plate up here, and then we also have the Cocos plate, which is the oceanic crust. And Google Earth has provided us with a decently detailed image of the ocean floor here, and I can go ahead and draw in some of the features. So if I wanted to find the trench, I'm going to go where it's darkest along the edge. That's indicating depth. And so the trench here gets real shallow because there's a ridge actually right in here, a divergent boundary that's coming off like this. But it continues around along like this. So this is the trench. The upper plate always has the teeth on it, or has the TPs on it, or the little triangles on it. Okay, and then we have the accretionary prism, which is in here as well. And I'm going to just do that in green. So the prism is right in here. That's going to be the area where we have our accretionary prism all along here. These are sediments that are being scraped off of the ocean floor. Behind the accretionary prism, we're going to have our four arc basin. So in here, we find depositional zones, low spots between the prism and the volcanic arc, which are going to contain sediments that are coming off of the arc itself. Okay, so that's in this area here, between the trench or between the accretionary prism and the arc. And then behind that, we end up with the arc itself, which I'm showing in red here. So this is our arc, our volcanic arc. Okay. The blue is our four arc basin. The green is our accretionary prism, and then the red is actually the trench. Right, so that gets you a kind of spatial organization for what's going on. Now you're like, okay, well, what about the back arc region? Well, anything back here is going to be into the back arc. And you'll notice there is no stable craton behind us here because we're into another plate. So there's actually a combination of plate boundaries sitting back here that are separating the Caribbean plate from the North American plate. And so we won't worry too much about dealing with those right now. But we need a bigger continent, essentially, than Central America to give us that stable craton to look at. So here's an example of ocean versus ocean. If we label these plates, plate 1 on the right, plate 2 over here on the left, I can redraw our boundaries right here. So here's that plate boundary with the teeth on it. On the upper plate, we have subduction going on here, right? Notice that we've got 100 kilometers depth noted down here on the right. And what's happening down there is melting of the asthenosphere, which rises up and makes magma in these areas. All of these little either yellow and blue star patterns are supposed to represent earthquake foci within the Benioff zone. And so that's what this area is right in here. It's our Benioff zone. Okay. If we come back up to the Earth's surface, we can see, here's our accretionary prism or accretionary wedge. So again, that's all the sediments being scraped off of the oceanic floor that come from over here on plate 2. Okay, those are our pelagic sediments. And the forearc basin then is this low spot. We can see it a little better in this diagram. This contains all the sediments that are really coming off of the arc itself. All right, let me just do this in blue. I think it will help. Let's put the prism back in there. Let's put the forearc basin there in blue. Okay, so there's our forearc basin. Now we're coming back to the arc. So each of these little volcanoes represents that volcanic arc. And then back here we have the back arc, what this particular diagram calls the back arc region. You could call it the back arc basin. You'll notice there's a little patch of sediments coming off of the arc here as well. And depending on the subduction within the zone and the angle of subduction, we might actually see volcanism going on in the back arc region. So the ocean or the island volcanic arc, okay, is not vastly different in terms of the different processes. We see melting and magmatism. We see seismicity. We see the same features that are in this diagram that we see in the ocean to continent diagram as well. And if we go down to the Solomon Islands, we're off the coast of Australia. So here's the Australian plate, and the edge of Australia is right there, right? So that's the eastern edge of Australia. It's a passive margin, so it's not active. And the question that I might ask you, or you can ask yourself, is in this diagram then, if the edge of Australia is not an active plate boundary, what is an active plate boundary? Okay, and what kind of boundary is it? Okay, well, you can go ahead and pause it if you're still pondering it, but you want to look for the darkest areas on the map because those indicate the deepest areas, and the light-colored areas are the shallowest region. So it's shallow near the edge of the Australian plate, but it's deep out here, right, all along this edge here, and it's also deep here, right there. And so we actually have a couple different things going on. There's a subduction between the Pacific plate going on and the Australian plate. The Australian plate is getting subducted below, okay, the Pacific plate. And so this is a kind of complicated, a little bit of a complicated region going on in this area, but we have subduction going on. So the red line would be our trench, and it's a kind of big figure, but if we wanted to maybe pick a place to draw in the volcanic arc, in this case, we could actually go up into Papua New Guinea and draw a series of little volcanoes. So all of these little islands that are off the coast here or out in the middle of the Pacific Ocean, they're all volcanoes. Okay, and they're all volcanoes, and they're all related to this subduction zone that's going on. And so subduction is Australia is moving off to the north in this direction, kind of like that. Okay. The other features that we would expect, well, is there a back arc region? Sure, there is a back arc region. It sits, way back here. That's the back arc region. This is the back arc region in here. Okay. Is there a accretionary prism? Yes, there is. It's a little hard to see. It's going to be right in there, right in there. Now it's going to be small, and I'll tell you that the accretionary prism should be small in this area. Why is that? Can you sort of guess for a minute, or you take a minute to guess? Yeah, right. It's because there's not a lot of oceanic crust here, right? The sedimentary layer that's being scraped off is not very big, and this subduction boundary hasn't been active for a long time. So we're not going to get as many sediments. Will there be a forearc basin? Yeah, it is hidden, but there will be a forearc basin sort of between the accretionary prism and the volcanic arc. And I won't draw that on there because it will get too hard to see, but I might just add in a little line here. So we'll call it forearc. And not all of these features show up at every single type of boundary, but we're just trying to sort of set the stage for the kinds of processes that are going on at many of them. So then the next type of continent or collision zone is a zone where it's continent versus continent. And so the plate boundary here is along what we call the main central thrust, which is here. I'm showing it in green, okay, with India being subducted, or actually I should say India being pushed below Asia, but there is no subduction, right? So the difference here there's no subduction going on. There used to be subduction going on, but what has happened is that we have two plates of equal density, and when you have two plates of equal density, and they're especially one that is continental crust will never become dense enough to sink into the mantle. It doesn't matter how metamorphosed it becomes, it's not going to become of a sufficient density to sink. And so what happens is we end up stacking or thickening the crust to almost about 65 kilometers in this area. Okay, and this is what creates the Himalayan mountains, the Mount Everest, K2, but it also creates this very wide zone that we call the Tibetan Plateau. The Tibetan Plateau has an average elevation of 5,000 meters. Okay? 5,000 meters or 5 kilometers. So everything in the Tibetan Plateau is relatively high in elevation at 5,000 meters. There is a foreland basin. Notice that the foreland basin is here. There is no volcanic arc, so the foreland basin is off on our left-hand side. So if we label plate 1 on the right and plate 2 on the left, the foreland basin is in India. Okay, there is no volcanic arc. There is no accretionary prism during this type of collision event. There is a foreland fold and thrust area, and so there's quite a bit of folding and metamorphism and some melting of the continental crust, and that's happening in this area here where you have these pink blobs. Okay. And so there's what we call a foreland fold and thrust belt. Right, so vastly different in terms of its anatomy, right? We have a foreland basin, we have high mountains, we have very thick continental crust, we have a foreland fold and thrust belt, we have a plateau, okay, and then that's it. Those are the main features, as well as a large number of really deep thrust faults that are running through here. We take a look at the Indian plate as it's colliding into the Asian plate. That should be ASIAN, not AISIAN. Sorry about that. Cross that out. The boundary here, the main central thrust through the system is right through here. And we have these little indentions here. This is the upper plate as India is going below Asia, so we'll put the teeth on the upper plate here, 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 and here. All of this back in this direction is the Tibetan Plateau. The foreland fold and thrust belt is here. So this is where our foreland fold and thrust belt is out here. And then the foreland basin is out here. So there are foreland basins out in the front of all these high mountains, which are made, the mountains themselves are sort of held up by all this tectonic activity and this thrusting. And then you have stable craton, So out here in the middle part of India, out even down towards the southern tip of India, you have a stable craton. That's not the case in Asia, where you've actually got in the Tibetan plateau, you'll have lots of faulting, lots of deformation, lots of seismicity in those regions. There's a number of different kinds of faults which have developed and evolved because the topography is so high. Okay? If we move on to talk about transform and divergent boundaries, in terms of their anatomies, they are commonly connected or linked together. And in this diagram on the right here, I can draw in a boundary for the plate. So plate 1 or plate B, they've actually labeled them for me here, plate B and plate A. And I have different kinds of boundaries connecting up to make this single plate boundary. We've got transform boundaries, which connect up ridge segments, spreading here perpendicular to the direction, or sorry, to the spreading is perpendicular to the boundary itself, or to the plate boundary. We have seismicity that is active at the ridge. What else is going on at the ridge? Well, we know we have magmatism because we have new crusts being made. And then we have seismicity at the transform boundary, but we don't have a lot of metamorphism. We don't have a lot of new magma being produced. We have plenty of hot rock here at the mid-ocean ridge, and so that means it's a good place to have hydrothermal alteration going on and certain kinds of metamorphism happening in those regions. At the top of the plate boundary, at the top of the mid-ocean ridge, you have a down drop block of rock. So if I draw a side view of it here, this central part of the rock has dropped down and you have a series of little faults here. And that down drop block, which can be quite deep, maybe even a kilometer or so, maybe even a little bit more than a kilometer deep, is the location where you have your magma coming up, right? So you're building new crust there, as well as hydrothermal vents and a number of other features associated with the mid-ocean ridge. If we come off to the left of the diagram here, we've got an interesting set of boundaries. We've got something called the Mendocino Triple Junction. I'm drawing this. I'm just do it in red. Red's a little easier to see. So that's the Mendocino Triple Junction that I've just drawn in red. And so we've got a convergent boundary in a subduction zone. So up here in Washington, Oregon, Northern California, we expect volcanoes chained all the way down like this. But then we get down into the area where we have the San Andreas Fault. And so we've got a transform boundary coming off of the Mendocino Fracture Zone, and the San Andreas makes a transform boundary. So we have 1, 2, 3 different plate boundaries coming together at that particular location, and then we can trace the San Andreas Fault all the way down into the Gulf of California or Baja area, and it goes offshore into the Gulf and hooks up with a divergent boundary down there. And so we see the Baja California sort of spreading off in that direction relative to the rest of Mexico, which in relative terms is moving off to the right. Okay, so we have a combination of features coming together. The San Andreas Fault is unique in this location compared to the transform boundaries on the right-hand side here, because while it is connecting up mid-ocean ridge segments, it is cut through continental crust, and the transform boundaries on the right have only cut through oceanic crust. And to cut through continental crust, it ends up creating a zone of intense seismicity, typically shallow level, less than 70 kilometers in depth, but at a range of magnitudes, ranging from small magnitudes all the way up to 7s and 8s would not be uncommon or unpredicted. Okay. Where do we find this kind of boundary going on, a series of transform boundaries and mid-ocean ridges. Well, we can come out to Iceland, where we have, again, our Asian plate and our North American plate, or the Eurasian plate, I should say, on the right-hand side. So we have plate 1 over here and plate 2 over here. And then we have a series of ridge segments that cut through something like this, and that creates the Mid-Atlantic Ridge, and they're connected up here by transform boundaries and fracture zones, which connect all these segments up and act to sort of adjust and realign, keep the plates realigned, and that boundary can be traced all the way up into Iceland, and that is actually also a hotspot. And then it continues on up past Iceland as well, up there. So this is a divergent boundary, and this is divergent. But every segment of this divergent boundary is connected to one of these transform boundaries. All right, so if we talk about making a summary here of what's going on, we're looking at a subducted crust. Actually, let's just change colors quickly. And we're looking at subducted oceanic crust and continental crust, creating our volcano here. And this guy is going to come down like this. Okay, and so we're at a situation where we have ocean to continent. And what kinds of processes are going on here? Well, we certainly have magmatism. We've got subduction. We've got seismicity or earthquakes. And we've got metamorphism. Okay, and both regional dynamothermal, so sort of large-scale metamorphism, but we also have hydrothermal metamorphism. If we come over to the right here and we just draw in a different color, we've got our volcanic arc here, which is cutting through not thick crust but thin crust. So here we have ocean crust to ocean crust. Okay, we have many of those same processes: magmatism, subduction, earthquakes, metamorphism, all going on at this location. If we draw a little boundary in here, okay, and we did, let's say, a Tibetan Plateau scenario where we've got India subducting into, there we go, or which has been subducted into and is being pushed below Asia. We see different kinds of processes. We don't find an arc. We don't find the same kinds of basins. We don't see an accretionary prism, but we do see lots of earthquakes. Okay. We would see metamorphism. Those would be common features when we're dealing with continent and continent collision. Okay. If I go ahead and just briefly erase this, it's awfully squeaky. Almost there. All right. So go ahead and erase that more or less, and we can draw a few more of these guys in here because we got both our divergent boundary to worry about, right? And so that is shown here in cross section, where we've got the crust, and then we've got the uppermost mantle, or the mantle lithosphere. So that's the mantle lithosphere, that's the crust, and together they make the lithosphere. Okay. We've got right up in here, we've got a magma chamber. So we have magmatism going on at these boundaries. We have ocean water up above, right? So ocean water, ocean H2O, which is sinking down into the subsurface below the into the crust at least, and so that gives us this hot magma chamber juxtaposed close to this ocean H2O. So we'll expect to find hydrothermal alteration, or metamorphism. Right? Would we expect to find seismicity here as the crust is breaking? Sure, we'll expect to find earthquakes. More so if it was pulling apart the continental crust, and we'll expect to find magmatism. So kinds of volcanoes. Okay? And then last we have the transform boundary. We'll do that off to the right here. So the transform boundary is really got some different features associated with it. It's commonly happening or adjacent to a mid-ocean ridge. Certainly we would have crust up top, and we would have mantle lithosphere down at the bottom, and we would not see magmatism. We wouldn't necessarily see a lot of metamorphism. And why is that? Well, most of the plate motion is side to side. It's not up and down. Whereas at the divergent boundary, we see hot magmas rising up through the asthenosphere, or hot rock rising through the asthenosphere, up into the create a magma chamber below the mid-ocean ridge. But we would see a lot of earthquakes. At this kind of boundary, and potentially you could see some magmatism. It's not entirely separated from the divergent boundary, so it's not that precise. But just in general, this gives us a summary of boundaries and the various processes that are going on at those boundaries. And we'll be moving on in the next segment, sort of to wrap up this lecture, and to talk about what gets these boundaries to move.